In today's video, we will be discussing about theory of computation. So, we are moving to a very fascinating subject, theory of computation. Now, what is theory of computation? Theory of theory of computation has three big deals. First, automation. Second, formal language, and third, we will be discussing about grammar. So, what is automation? Automation is formal mathematical construct. Think of it like an abstract machine. It is some input. It may produce some output. It might have some memory, and it can make decisions based on its current state. When we say abstract machine, we mean we don't care about hardware or wire. We care about logic of how it works. So, what is automation first? We will write this as abstract model that accepts input and produces output. It has storage and it makes decisions. Now, talking about formal language. A formal language is a set of sentences or strings formed from set of symbols according to a strict rule. It's not like English, there is no ambiguity, but in formal language, rules are precise. So, formal language is set of sentences formed from symbols by formal rules and what is grammar? Grammar is a set of rules used to generate the sentences of a formal language. Grammar tells you exactly which string belongs to the language and which don't. So, grammar is rules for generating sentences in formal language. Right. Now, what is computability and what is complexity? So, what kind of problem can a computer solve in this principle? That is computability. And problems which can be efficiently solved in practice, that is called complexity, right? So what we will write about complexity and computability? Complexity and what is computability? Computability is what computers can solve, and complexity is what computer can solve efficiently. Now, before going to the next stuff, we need to make sure everyone is comfortable with some mathematical tools. So, what is set? Set is collection of distinct elements, variety of elements. We use operation like union that means set A and set B, both I can consider elements. Intersection, that means only those elements who present in both set A, set B. Difference, that means set A has these elements, set B has those elements. this minus those and complement, that means both sets combine to give a certain amount of complemented set. Now we talk about functions and relation. So for that we will understand difference between total function and partial function later on. Right. So first of all we will go to the basics. So every formal language is built on alphabet. Every formal language is built on alphabet, denoted by this symbol. For example, this containing two symbols A and B. And what is string? So string is a finite sequence of symbols from the alphabet. So a string is what? Finite sequence of symbols from the alphabet. Finite sequence of symbols from alphabet. Right. Now, a string in a language is called sentence, and there are certain operations. Right. For example, concatenation. Right. So concatenation is when I join two string together. Suppose I am erasing this. Right. So let's discuss about operations. Right. So first we will discuss about concatenation. Suppose I have two strings, that is B is equal to ABA, and under a string W is equal to ABAA. Now I concatenate these two strings, I will get BW, I will get ABA, ABAA. As simple as that. Now I have to reverse a string. So suppose this is my string, I will reverse it, I will get ABA. Right? Now I will perform repetition. What is repetition? Repetition means a string concatenated with itself. Suppose I am writing this a square. This is concatenated with itself, right? And suppose I write b0, b to the power 0. That is nothing. So this is lambda, the empty string. So a question arises, what is empty string? This denote the string which has its length 0. That string is called empty string, right? It has no symbol. Now length. So we know from here, by for length we do this symbol. Length of V is what? 3, right? Now Moving on, definitions of formal language. So, what is sigma star? Sigma star is set of all possible strings you can form using symbols in sigma, that is alphabet, including the empty strings. Right. So I can write this as all strings and including lambda and sigma plus, this is the same but without empty string. So basically this is sigma star minus lambda. Right. A formal language is any subset of this sigma star, all strings including lambda. So you can pick any collection of a string and call it as a language, as long as those strings are made from your alphabet. As far as those strings are made from alphabet, this is very crucial point. So suppose I have a language 1, right, written as a to the power m, b to the power n, and n greater than equal to 0. Right. So this is language of all strings with some number of a's followed by some number of b's. So it can be lambda, it can be ab, it can be bb, it can be bb, right, and so on. Suppose there is language 2, a, much simpler, just two strings. Each string in a language is called a sentence of that language. So this is sentence of language 2, this is sentence of language 2, this is sentence of language 1, this is also sentence of language 1, and this is also sentence of language 1. Right. Performing operations. So how I will perform operations? Union. Right. I will write this. I will perform union. So what I will get? This has lambda, this also has lambda. So we will first get lambda, then this has AB, this language 2 has string AB, language 1 has also string AB, so I will get AB. Then all those things in language 2 and all those things in language 1, all. So each and every element present in language 1 and language 2 are there in the union, right? So I can write basically a to the power m, b to the power n, right? And then intersection. So if we talk about intersection, that is L1 intersection L2, I will only get only a string that are in both languages, right? So it is only A, B. Difference L1 minus L2, that is if I want difference, strings that are in L1 but not in L2, right? So I will remove those in L1 that are present in L2. So I will remove this was matching. So I can simply write as lambda AB. I will not write because here it is getting subtracted. ABB, ABBB, and so on. Right. And complement. Complement is all strings over sigma star that are not in L2, right? So in language 2, right, all strings over sigma star that are not in L2. So L2 has AB and A, L1 contains AB but not A. Right. So L2 minus L1 is your A. Right. L2 minus L1 is your A. Right. Now we will go on the next topic. Let me erase this. So let's talk about some more special operations. Reverse. Take every string in the language and reverse it. Right. Concatenation, we also found it. And for example, I had my L1 and L2 as right. And then if I have to reverse, so L2 reverse will be written like, it will be AB, right? And then concatenation of two languages. So I will take every string from L1 and every string from L2 and concatenate them in all possible combinations. So L1, L2 will give me A, right? It will give me AB, AA, and then A, B, B, A, B, 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 and so on, right? Basically, I can simply concatenate them with this, right? All possible combinations. So how can I concatenate every string? So I can first take A, B, A, then it's concatenation with lambda, right? Now it's concatenation with AP and AB, right? And then with AABB, AABB, and so on, right? Concatenation of language with itself, that would be L square. I mean, that would be simply AB, all possible combination we will take AB, and then AA, right? And star closure. This gives all possible concatenation of strings from L2, including the empty string. So basically, this star closure is written as L2 0 union L1 union, and then right. All possible concatenation of strings from L2, including the empty string. Right. Positive closure. Same, but starting from L to 1. This will be your positive closure. So I have a question, find L2 minus L1. Reverse. So L2 minus L1 will give me AA. Reverse of AA will give me AA again. Right. Now, going on grammar definitions. So I am again erasing this. Now, let's talk about grammars, the rules that generate in a language. So, grammar has 4 components, right? Variable, symbols, also called as non-terminal symbol. These are like placeholders. They get replaced. These can get replaced. Act as a placeholder. And then terminal symbols. Actual symbol that appear in final string. Final string. And start symbol. From here, every derivation begins. And then set of production or rules. It will tell how to replace a variable with something else. How to replace a variable with something else. Right. So let us take an example. Here V is equal to S and T equals to AB, and productions are S, A, S, B. It means replace S with string A, S, B. Right. And S to lambda means replace S with empty string. This is the grammar that generates the language the same L1 that we saw earlier, right? It will cause this, replace S with A, S, B. So this will be, and again S with, so this will be again, and again replacing S with string A, S, B. This will be like and then replacing s with empty string. So this is we will get. So this will generate this language, right? Now deriving string. So how do you use a grammar to generate a string? Through this process called derivation, we can generate a string, right? Through the process derivation, we can generate a string. We will start with symbol s, then we will apply any applicable production rule, replacing a variable with what is on the right side of rule. And we will keep doing this until no variable symbol remain, only terminal variable. So one example is, we will start with s, apply s asb, so this will be asb, and then apply s asb again, then we will get aasbb, and then applying s lambda, so we will get AABB. The same we did here, right? And we can repeat this as many times as we want to get AABB, and so on. Or we can stop early, applying S lambda right way, we will get the empty string, right? From here, we can get empty string, right? String. Now, let's talk about language generated by grammar. So I'm erasing this again. So we will talk about language generated by grammar, which is written as LG, right? So LG is the set of all terminal strings that can be derived from a start symbol. Not just only one string, all possible strings that can be derived. To prove a language equals LG, we need to show two things. Every string in L can be generated by grammar. That grammar will generate every string in that language. And second, every string generated by G is actually in L. So every string generated by G is in the language, right? And then finally, let me tell you about automata. Automata is an abstract model of digital computer which has input mechanism and control unit and storage mechanism. Input mechanism reads the input, usually character by character, and control unit is like a brain which can be in different states, and then a storage mechanism is like a stack or tape, possibly an output mechanism also automaton can have. Output mechanism. Now, control unit moves from a state to a state based on what input it reads. This movement is governed by transition function which says if I am in a state x and I read symbol y, if I am in a state x and I will read symbol y, I will go to state z, right? So this was all it is, and some applications also. Programming language use grammars and automata all the time. When you write code and compiler checks if your code is syntactically correct or not, it is using a grammar or an automaton to do that. The grammar describes valid identifiers, valid expressions, valid statements, and automaton parses your code against those rules. If it does not match, you will get an syntax error. Right. So this is all for today.